All right, so I've had a number of similar questions on Chapter 3. So I just want to go through setting up first law balances for a couple of different special situations that come up a lot. And then we can look at the special case of an ideal gas. Right? And hopefully this is helpful. All right, so the first case that I want to look at is when we solve problems that are isochoric in nature. Right? So isochoric. And let me make a note. So we're looking at Chapter 3, okay, first law balances. Okay, and we just want to make sense of some of our special cases. So the first case is isochoric. Okay, and good news, I've got a new stylus on order, so I apologize for some of this handwriting. So we have an isochoric process. Isochoric means constant V. Okay. When I'm dealing with an isochoric process, right, the key word to identify that I have an isochoric process in the problem statement is typically of the nature that I have a rigid, closed tank. Okay, so if I have a rigid container or tank, that means the total volume is not changing. And if it's closed, that just means no mass is coming or going. Right? So the extensive total volume is constant, and then the molar or specific volume is constant. Okay. So the first type of problem that we'll look at, the first type of special case we'll look at is this isochoric process, which corresponds to constant V. You're going to look out for keywords, such as rigid closed tank. And so, one scenario might be that you have some process where, say, the initial temperature and pressure, and then maybe the final pressure, and you're asked to calculate, say, I guess in this case you're asked to calculate Q, right, the heat required for, this expansion or compression process. All right, so how do we go about solving this? Okay, first thing is if I look at my initial state, I know my temperature and pressure. So remember, for a single component, single phase system, I have 2 degrees of freedom. Okay, so I need to specify 2 intensive properties, at which point everything else is fixed. Right? Think of my superheated steam tables. If I know temperature and pressure, I can go to my superheated steam tables and read off everything else I could possibly want. Okay. So if it's a superheated steam, right? I know T and P. I could go to my steam tables. I could look up specific volume. I could look up internal energy and everything else I could possibly want. Okay, so let me write down, say, U1. You could write down H1 and S1 as well. All right, so then key is, so rigid closed tank, so volume's constant. So I know all of these, right? My final state, I know P2. Okay, well, if it's a single component, single phase system, and I need something else, right? In this case, I know V, and I know V2 is going to be equal to V1. All right, now how do we go about solving a case like this? Okay, so I'm going to start by writing down my first law balance. Okay, so I'll have the delta U is equal to Q plus W. Okay, so delta U isn't a problem. If this were the steam tables, right, I know P2, V2, right, I could go to my superheated steam tables, read across my pressure column until I find 2 temperatures that have volumes that bracket my volume of interest, right, interpolate and find, temperature, internal energy, and everything else. Right, so delta U is not a problem. Okay, but let's look at W. Okay, so remember in this book, right, the 2 types of work that we're going to look at are that we could possibly have are shaft work and boundary work. Shaft work, if shaft work's present, it'd have to be explicitly stated in the problem, and then you'd have to be given, say, how much work is being done on or by the system in this form of shaft work, or you'd have to be given a way to compute it. So typically in this book, in this course, we'll reserve to just looking at PV boundary work. Okay. All right, so for this case, all right, so if I have boundary work, my working equation is W is equal to negative integral of P dV. Okay, that's a V. All right, integrate from my initial to my final state. Now, key here is volume's constant. Volume's constant. Volume's not changing. So dV is 0. So my work term is 0. Right? My system's not expanding or contracting at all. Okay, so my work for this isochoric case is 0. Therefore, my first law of balance just reduces to delta U is equal to Q, where delta U, okay, we can get that in one of two ways, right? One is if this were the steam tables, delta U would be equal to U2 minus U1. Okay, and U1, right, I have, because I know TMP, I look it up, say, in my superheated steam tables. And then for my final state, since I know P2 and V2, if it were superheated steam, I would find my pressure, read across my volume row until I find two volumes that bracket my value of my volume here, and then you'd have to interpolate to find U. Okay, so you can calculate delta U, and then once you have delta U, right, you have Q, since Q is delta U. The other scenario is, especially for the ideal gas problems that you have in your quiz, is that delta U, okay, is equal to the integral of CV dt, where you're going to integrate from your initial to your final state. Okay, now if you have an ideal gas, right, in general, even for an ideal gas, CV is a function of temperature, and there's polynomials given in the back of the book. Okay, if though CV is constant, which is what appears on the quiz, just to make it easier on you, okay, then CV is constant, so I can pull it out of the integral, and I just get the delta U is equal to CV times T2 minus T1. Okay. In general, all right, CV is not independent of temperature, so you'd have to integrate it, but, right, in general, we'll assume that it's, or here we'll assume it's not the case because that's what shows up on your quiz. Okay. So that's our isochoric process. Okay. Let me add a new page and let's go to the next one. Okay, so that's isochoric. We'll also look at isothermal, isobaric, and then adiabatic is the one that comes up. Okay, so that's isochoric. Which one should we look at next? Let's look at isobaric. Okay. Okay, isobaric means constant P. All right, so isobaric means pressure is constant. So how do we handle this situation? Or first, let's think about keywords. So what keywords would I have to suggest that I have an isobaric process? So in general, right, so we said isochoric, you're going to have a closed rigid tank. The picture I have in my head in general for an isobaric process is a piston cylinder apparatus. Right, so I have a closed system in which I have, say, you could think of it as, say, your top wall, right, is able to move up and down, or you have a piston head, right, that's able to move up and down, so that your system remains at a constant pressure, right, where that pressure, if the piston head's weightless, is equal to the pressure of the surroundings. So in general, isobaric processes, I think of a piston cylinder apparatus. Okay. All right. So if I have an isobaric process, let's go through a scenario for this. It may be that I have, a system at, say, an initial temperature and pressure, and I'm going to take my system to some new temperature T2. Okay, and it's an isobaric process, so I would know that P2 is equal to P1. Okay, now I'm just going through some hypothetical different types of problems. Your problem might change, or you may have different information given, but setting up the first law and the basic working equations would be the same. Okay, and it may be that, so in this case, we'd want to calculate maybe, say, W and Q. Okay, so let's go through this animal. Okay, and we'll get to the final equation that we use a lot, that just for an isobaric process, Q is equal to delta H. Okay, but one step at a time. All right, so first let's think about, so our first law of balance in general is going to be delta U is equal to Q plus W. Okay, so just like before, let's start by looking at Q and W. Okay, I'm going to start with W. And so again, okay, we'll assume just that we have PV boundary work. So W is going to be the negative integral of P dV, where I'm integrating from my initial to final state. So key here would be for an isobaric process, is that my pressure is constant, so I'll just bring my pressure out. Okay, and actually just to make my notes clear, I'm just going to say P2 is equal to P1 is just equal to P. All right, let's just drop subscripts. So W's integral of negative integral from 1 to 2 P dV. P is constant, so it's negative P integral from 1 to 2 dV, and that's just negative P times V2 minus V1. Okay. All right. So W then, okay, is equal to negative P V2 minus V1, or if I wanted to expand it out, that's negative P V2 plus P V1. Okay. All right. So now I want to do something. All right. So if I go back to my first law of balance, we had delta U is equal to Q plus W. Okay. And what I'm going to do is I'm going to solve for Q. So Q is equal to delta U minus W. Okay. Where, okay, just focusing on this right-hand side. So if I have delta U minus W, I'm going to rewrite delta U is U2 minus U1. The minus W, okay, so I'm going to plug in this equation here. So it's a minus. So it's going to be plus PV2 minus PV1. So grouping terms, I'm going to rewrite this as U2 plus PV2 minus U1 plus PV1. Okay. U is a state function. U is my internal energy. P is my pressure. And then V2 is my either molar or specific volume, which likewise is just a state function. So U, internal energy, is a state function. U plus PV is a state function, which leads to the definition of a new thermodynamic state function. Oftentimes we call it as a convenience function. It's introduced for convenience because it appears a lot and simplifies our calculations. But we're going to define a new quantity, enthalpy, and enthalpy is defined as being U plus PV. Okay. So Q is equal to delta U minus W, okay, where delta U minus W for my isobaric case is equivalent to delta H. Okay. So oftentimes for our isobaric case, all right, we'll just write down the Q is equal to delta H. Okay, and then W, we have W is equal to negative P times V2 minus V1. Okay, and if you wanted to, okay, this is, delta U minus W, right, is equal to delta H. So you could just as well get, let's see, W would be delta U minus delta H, right, if you wanted to go that route. So you can get Q and W in that way. Again, you could just as well get W if you wanted to. From here, delta U minus W is equal to delta H. So W would be delta U minus delta H, all right, if you wanted. Okay. Cool, right? And delta U is delta U. Now, in case one, if we had, say, steam, if we were using the steam tables, then again, from the problem statement, right, I know T1 and P1, I know T2 and P2. So the state of my system, if I'm thinking of a superheated vapor, is completely specified. So I go to my superheated steam tables, and I could find H1, H2, V1, and V2, and with that I could readily calculate Q and W. Right, so I would readily go and look up, in this case, H and V in my steam tables and calculate Q and W. Right, so Q delta H is H2 minus H1. Okay, if I had an ideal gas, right, in the case of an ideal gas, okay, where things change is for an ideal gas, right, we would say that delta H is the integral from my initial to final state Cp dt, where if Cp is constant, all right, then I end up with, a delta H is Cp T2 minus T1. Okay, but in general, even for an ideal gas, Cp is a function of T, right? So you'd have to integrate that. Okay, and likewise for an ideal gas, right? Just for completeness again, delta U, integral from 1 to 2, Cv dt, and if Cp is constant, then I end up with delta U is Cv T2 minus T1. Okay. All right. Yeah. Okay. And so I'm just, looking at this in the context of our problems in this course from chapter 3 in terms of trying to help out. So we have isochoric, we have isobaric. What I look at next is isothermal. Okay, so let's look at an isothermal process. Isothermal means constant T. All right, so isochoric, rigid tank, volume's not changing. Isobaric, piston cylinder. All right, so my boundary is able to move up and down so that my pressure remains constant. Isothermal, temperatures remain constant. So the picture I typically have, here in my head is, maybe my process is taking place in some huge, liquid reservoir, some huge thermal bath that's able to, regulate or maintain, absorb heat or give heat and maintain a system at constant T. So if we have an isothermal process, so isothermal constant T. So let's think about this one. So let's imagine again, I have some system at T1 and P1. Okay. And I'm going to take that to some final pressure P2, which is specified, and then T2 is going to be equal to T1, it's going to be equal to T. Okay, so another situation in which the state of my system is known, is specified. Okay. Let's go through this case. Okay, so if I write down my first law of balance again, okay, delta U is equal to Q plus W. When I think about delta U, okay, delta U, right, it's a state function. So in my initial state, I know temperature and pressures. Single component, single phase system. If say we're superheated, the state of my system is fixed. I could go to my superheated steam tables. I could look up, find that T and P, and I could look up U1. Likewise, in the my final conditions, I know temperature and pressure. I could do the same thing. I could go to my steam tables. I could find U2. So I have delta U. That's not a problem. Okay, so again, let's look at Q and W. So I want to look at W. Okay. So W, okay, again, thinking just in terms of boundary work. So W is going to be the negative integral from my initial to final state PdV. So now when I evaluate this integral, okay, what's key is I need to know how P changes with respect to V. In general, when I think about a single component, single phase system, I have 2 degrees of freedom. So what that means is you could think my intensive properties are a function of 2 variables. Okay. In this case, I'm fixing a intensive variable T. So P then is only a function of a intensive variable, right, which I can relate to V. Okay, so since I have a constant temperature process, right, I should be able to find a relationship between P and V and integrate this animal. Now, okay, we can think of this in 2 ways, and we've kind of seen both in this course. Is one, we use the steam tables. And so if we had a superheated steam, okay, what we could do is, so say we had an isothermal process for superheated steam. We would look under a column, right, with the header of temperature, and we have, say, we know what our initial and final pressure is. So what we would tabulate is volume as a function of pressure, at that constant temperature column, right? So constant temperature, we would tabulate data for P versus V, and then we would numerically integrate it. Okay, so the steam tables, you would tabulate PV data and numerically integrate. Now, for the case of an ideal gas, Okay, we have an analytic relationship between P and V. Okay, namely for an ideal gas, we have our ideal gas equation of state. So for an ideal gas, we know that PV is equal to RT. Okay, so solving for P, I know that P is equal to RT over V. So if I come to my work expression, okay, so W is a negative integral from 1 to 2 P dV. Okay, so what I'm going to do is I'm going to plug in my relationship for P. That's RT over V. Now R's constant is my molar gas constant, and since I have an isothermal process, temperature is constant. So this is minus RT integral from 1 to 2. Oh, and I forgot dV here. Integral from 1 to 2, 1 over V dV. Okay, so integrating then, I get that W is equal to negative RT log V2 over V1. Okay. Now this equation here, as I've written it, right, this is only the case for an ideal gas, right? So only for an ideal gas, which is described by the ideal gas equation of state. Okay. For a real fluid, such as water, right, in that case we could numerically tabulate P versus V data at that constant temperature and numerically integrate. Okay, so now this equation, okay, so here I'm using molar volumes, a ratio of molar volumes. In this problem, in this problem we could solve for V1 and V2, right? Likewise, using the ideal gas equation of state, we'd have V is equal to RT over P. You could also simplify this equation to work with P, okay, and this would work in the exact same way. Key is just that P1 V1 is equal to, I'm just going to write as RT since temperature is constant. P2 V2 is equal to RT. And so therefore we get that P1 over P2 times V1 over V2 is equal to 1. So that V2 over V1 is just equal to P1 over P2. Okay, so this is equivalent to negative RT log P1 over P2. All right, and as a sanity check, if my system's, if it's an expansion process, so V2 is greater than V1, so this is positive, okay, so this is greater than 1, so the log term would be positive, negative sign, work done by my system, right? If V1 is greater than V2, this is less than 1, the log term's negative, it takes a positive form, it's work done on my system, and you can go through the same exercise with respect to P. Okay, so for my isothermal process, okay, we said you could get U, right, because the state of my system's fixed. I could get W, I may have to use the steam tables to numerically integrate PV data, or for an ideal gas, right, I could work it out or integrate it this way. Okay. And then again, just for completeness, I'm going to make the comment for delta U. Okay, so one case would be, say, using the steam tables. All right, look up U1 and U2, and then you could compute the difference. Case 2, all right, would be, again, delta U is integral from initial to final state CV dt. And if you're told that CV is constant, right, you can get CV times T2 minus T1. And so then, in this case, to get Q, okay, Q you would just get from your first law of balance. Okay, so to get Q, it's delta U is equal to Q plus W. Therefore, Q would just be delta U minus W. All right, so since we said we can get delta U, we know how to get delta U. In this case, we can get W, we can get Q that way. All right, so far so good. Things are going well. All right, now let's look at the last scenario. Okay, so the last scenario you want to look at is an adiabatic process. Okay, an adiabatic process. And so, again, we'll have a system in which say we're at T1 and P1, and we'll perform some work or have some work done on us, and we'll go to, so maybe it's a compression or expansion process until we get to final state at some P2. Okay, adiabatic, okay, means that Q is equal to 0. The picture I have in my head for an adiabatic process is my system is, say, wrapped in styrofoam or insulation so that there's no heat exchange between my system and surroundings. Okay, so in an adiabatic process, I think of my system as being perfectly insulated so there's no heat exchange between my system and surroundings. Okay, so here again, my initial state is fully specified. I know T and P, so I could look up U, H, S, whatever else I want. Say if we're water in the superheated steam tables. But in my final state, I only know P2, right? So one thing I'm going to need to do is I'm going to need to pin down another intensive variable for that final state. And then once I have that, then I have everything. Okay, so let's see how we might go about that. Okay. All right, and I'm going to try and flow one way the natural progression based on the problems we've done so far. Then I'm going to pause because we'll get stuck and rewind. Okay, so bear with me. All right, so I'm going to start by thinking about my first law balance. Okay, my first law balance is going to be delta U is equal to Q plus W. Okay, where here Q is 0. It's an adiabatic process. So I just get that delta U is equal to W. Okay. Now the challenge is I just can't directly, apply this equation, right? Well, so I'm going to write down two things, and I'm going to get stuck in two ways. Okay, one is if I just think about delta U. Okay, one option, again, think in terms of my steam tables. Okay, so I can go to my steam tables. If I could. To go to my steam tables to calculate delta 2 or delta U, I need U2 and U1. The challenge is my initial state's fully specified. I know T and P. The same's not true for my final state. All I know is the final pressure. I don't know the final volume, right? I'm not told it's isochoric. We don't know the final temperature. We're not told it's isothermal, right? All we're told is the pressure and that it's adiabatic. So, I can't go to my steam tables, right, and find U2 because I don't have a second intensive property to fix the state of my final system, right? So there I'm kind of stuck, right? I could also think in terms of, well, delta U is going to be equal to the integral from my initial to final state CV dt. Okay, here again I'm stuck though because I don't know my final temperature, right? I don't know T final, right? So I can't readily evaluate this term. I could look at W, right, and think about boundary work just like we've done so far. And so if I think about, PV boundary work, then W's negative integral from initial to final state PdV. Okay, my challenge though here is I can't compute this. And so my challenge is again, it's single component, single phase system. I have 2 degrees of freedom. So I could think of my intensive properties as being a function of 2 variables. Okay, so this process isn't done at constant temperature. It's not done at constant pressure, right? And so pressure is still a function of 2 variables. And so this is where we say, mention that work is path dependent, right? And so I don't have a relationship just. I can't work out a relationship just for P with respect to V that would allow me to integrate this equation, right? Temperature's changing, pressure's changing, volume's changing, right? So I can't go to my steam tables and say assume temperature's constant and tabulate data and numerically integrate. All right, it's not going to work. Okay, so I can't just calculate W, right? And not only that, I would have no idea about my final state because all I know is P2. I don't know V2. Okay, so I'm stuck again. Okay, so this is where we're going to take a step back and we're going to change this problem up slightly. Okay, all right. So I'm going to say let's rewind. And so the trick that's, well, not trick, but what's not necessarily obvious or clear is I have my first law of balance here, right? And what I'm going to need to do is write it in differential form. And so the key to remember is when I have, differential, it's like, what is the differential of f? Or what is, say, delta f? If f is some arbitrary state function, right? F is equal to, say, f in state 2 minus f at state 1. And that's going to be the integral from my initial to final state df, right? It's the integral of my differential, where df corresponds to some, infinitesimally small change in f. So, I have delta U, right? I write it as delta U because it's a change in internal energy. It's a state function, right? I don't write delta Q and I don't write delta W because they're path functions, right? So deltas just don't make sense because they're path dependent. Okay. So, this, right, is, would correspond to, an integrated form, for lack of a better word. If I write my first law in differential form, right, it will take the form of du is equal to, okay, so the book just usually writes dq. Often I'll write del q just to remind myself that it's a path function, plus del w, right? So just in general that they're path dependent. So now that I have written down in differential form, okay, what's key still is I have an adiabatic process. So dq is 0. Okay, so my differential form of my first law reduces dq is equal to del w. All right, so I could keep that as du, that's fine. Okay, what I'm going to do next though, and so let me make a note here, is that I'm going to be thinking about ideal gases, right? Right now I'm going to be thinking about ideal gases, and then we'll come back to the steam tables. Okay. Start by thinking in terms of an ideal gas. All right, so what I'm going to do, okay, is I'm going to take du, my differential for u, and that's equivalent to Cv dt. Okay, Cv being my constant volume heat capacity. And then when I think about work, remember this is a differential change of work. I'm going to assume I just have boundary work. So I rewrite this as negative P dV. Okay, and so again, right now I'm thinking I'm going to work out expressions thinking in terms of an ideal gas. All right, so how I'm going to work out expressions thinking in terms of an ideal gas is I'm going to use my ideal gas equation state. So namely PV is equal to RT. So solving for P, I get V is equal to RT over P. Okay, so plugging that in, I have that CV dt is equal to, and I said I need to solve for P. P is equal to RT over V. So Cv dt is equal to negative RT over V dV. Now, I couldn't just integrate this equation, right? I just can't say integrate this equation, right, to calculate my work. Reason being is, again, V's changing, as is T, right? T is not constant. As I go from my initial to final state, temperature's changing, volume's changing, pressure's changing, right? So I can't just integrate this with respect to V. All right. So the subtlety that's done, all right, so keeping this in my differential form, right, this is my differential form of my first law of balance, is I'm going to, you could just divide through by T. I'm going to divide through by RT just because CV and R have the same units, so I can make things dimensionless. So I'm going to rewrite this as CV over R, okay, and essentially it's RT, okay, but I'm going to write it as CV over R just because this is dimensionless, and that works out. dt is equal to negative 1 over V dV. All right, so then this, right, I could integrate, okay. So this I'll integrate from my initial to my final state, CV over R times 1 over T dt is equal to a negative integral from initial to final state, 1 over V dV. Right? Where for an ideal gas, CV is only a function of T. Right? So I could go ahead and I could work out an expression for this integral. Okay, cool. All right, what I'm going to do next, well, actually, let me start with this right-hand side term. This one's not bad. The right-hand side, it's just 1 over v dv, so that's negative log v2 over v1. All right, so what I'm going to do with the first term here, okay, is I'm going to assume CV is constant. So in general, CV is not constant. Even for an ideal gas, CV is a function of temperature. If you were to look in the appendix of the text, you would find expressions for CV of ideal gases written as polynomials with respect to temperature. So in general, CV is not constant. Okay, but by assuming it's constant, it's going to simplify this expression and result in a pretty nice, simple equation that we can use. I say that though because the text also does talk about, log mean, heat capacities and things of that nature. The goal is just, hey, if I have some temperature range, maybe I can take my heat capacity to be the average value over that temperature range, and then, if I assume it's constant in that value, I could simplify my equation as we're going to do here. Okay, log mean's a little problematic, but first we need the equation so you could see why it's problematic, and it's mainly because we don't know T final. So anyways, if we assume CV's constant, what that does for us then is CV's constant, R's constant. So I could bring out CV over R, integral from 1 to 2, 1 over T dt. So that gives me CV over R log T2 over T1, and that's going to be equal to negative log of V2 over V1. All right. So what I'll do next, okay, is negative sign. I'm going to use that to flip my terms, and I'm going to take advantage of log rules, bring this up as a power. So I can rewrite this as, okay, log T2 over T1, and that's raised to power CV over R is equal to log V1 over V2. And then next I'll take the exponential of both sides. So this becomes T2 over T1 raised to the CV over R is equal to V1 over V2. Okay, where this term's dimensionless, it's a ratio of volumes. This is a ratio of temperatures. It's dimensionless. CV over R is dimensionless. Okay, for temperature though, you just need to make sure you're using absolute units. All right, so this is true for an ideal gas. Ideal gas part in terms of using ideal gas equation of state to work with my differential with respect to V. So this is true for an ideal gas and assuming CV is constant. Okay. The book also gives a relationship using P. How we get P is using our ideal gas equation of state. Okay. So let's work that one out. So mainly, we know that P1 V1 is equal to R T1, and P2 V2 is equal to R T2. So V1 is equal to R T1 divided by P1, and V2 is equal to R T2 divided by P2. Okay, so V1 over V2 is equal to R T1 over P1, R T2 over P2. R's cancel. Oh, and that's a 1 there. And we end up with P2 over P1 times T1 over T2. Okay, so if I plug that in here, I get T2 over T1 raised to the CV over R is equal to P2 over P1 times T1 over T2. All right, so to further simplify, I multiply both sides by T2 over T1. So I have T2 over T1 raised to the CV over R times T2 over T1. which I'm going to make a note is equivalent to being raised to the power of 1, is equal to P2 over P1. Okay, this, I have the same term in parentheses. I can add the exponents. So I get T2 over T1 raised to the CV over R plus 1 is equal to P2 over P1. And then the last simplification made is again for an ideal gas. All right. For an ideal gas, we have that Cp is equal to Cv plus R. Okay. Therefore, Cp over R is equal to Cv over R plus 1. And so this we could just rewrite as Cp if we wanted to. Okay, and that's equal to P2 over P1. Whew. So now for this problem, right, if we had an ideal gas, okay, I know T1 and P1, I know P2, and then, presumably in the problem statement, we'd be given heat capacity, which you are in the quiz. And so, you could solve for T2, right? This gives you a way to solve for T2. Phew. Once I have T2 then, for my adiabatic process, then I could go back up here, right? And I could calculate delta U, right? Which is the integral from 1 to 2 of Cv dt, because now I know my final temperature, right? So for my case of an ideal gas, then I could integrate this term. All right? Cool. Easier said than done, right? But for the case of an ideal gas, adiabatic process, that's what I would do, right? Q0, so then I'd get T2, and then I could calculate delta U, which would give me W. Okay? All right. Now, if it were, so what would I do if it wasn't the case? Well, let's see. Hold on. Where am I? Sorry, I'm rewinding. So there's my adiabatic process. All right. So my first law of balance was just delta U is equal to W. So then once you know that final temperature, we can compute delta U without a problem. Okay. All right, so I hope that helps with the quiz. I hope that helps you make all the connections that you need. I'll post this notes along with this video, which is, already probably, too long or longer than you might want to work with. But I hope that helps and that makes sense, and that you can use that as you solve your problems. Okay, let me know if you have any questions.